Perfect. So, good morning, everyone. Welcome to the inaugural seminar of the Moore Foundation's EPiQS Postdoctoral Seminar Series. We plan to host these seminars once a month and hope you'll continue to join us. If you have recommendations for speakers, please feel free to share those with us also. Please also feel free to reach out if you have any questions, comments, or concerns. To start off this seminar series, we are delighted to host Shaowen Chen. Shaowen is a Harvard Quantum Initiative postdoctoral fellow working in the group of Professor Amir Yacobi. He's interested in studying correlated and topological properties of quantum materials using electrical transport and novel quantum sensors. Shaowen obtained his BS in physics from Peking University and his PhD in applied physics from Columbia University in the group of Professor Corey Dean. Shaowen has mentioned that he'd be happy to take your questions along as he goes with this talk. So please feel free to ask any questions. If you can hold off, please feel free to also write them in the chat and we'll bring them up at the end. So today we'll hear from Shaowen about imaging hidden states in Josephson junctions. And yeah, without further ado, Shaowen.
Okay, thank you very much, Mihir. And I also would like to thank all the organizers. I think this is a great idea to extend the wonderful discussions we had, in person for the more EPiQS series. Okay, so today I want to talk about our sort of recent work in specifically imaging the current flow actually in Josephson junctions. And since we're doing this over the cloud, I want to sort of start with something like kind of a bird view, right? So like as experimentalists, what do we do when we're doing some measurement? So for example, we have this sort of complicated object, right? And our measurement is like shining a light on this object and, casting a classic shadow, if you will, of this project. And if we do this, in this case, we may come to the conclusion or come up with a model of like pure happy physicist, right? But obviously we can see this model does not really capture the object we were censoring or we're trying to measure. And maybe one lesson we can learn from this is that, okay, so we have a global measurement, right? Like a light, but we're sort of missing the local details of the state. But more generally, I guess, we can try to do more measurements, measuring different observables that are orthogonal to each other, which will help us build a better model for the state we're interested in. So to be more concrete, right? So like we can take the example of our favorite, probe, which is electrical transport measurement. And we can look at a few examples here, right? So in this top row here, are sort of the pictures, right? The models we drew, so we think what's going on. And the bottom row here is sort of the electrical transport measurement that we use, that we observe to come, to sort of come up with the model. So with the benefit of hindsight, and I should say, maybe on the top here, there's what is actually going on, which is unknown, right? And maybe with the benefit of hindsight, we can say, okay, some of these measurements, some of these models are sort of more capturing what's going on, and some are not. But generally speaking, electrical transport has two problems, right? So for example, you cannot see the details between electrodes. And also if your state has zero resistance, just don't measure anything. Okay, so today my focus will be on Josephson junctions, right? Which is essentially a superconducting hybrid structure. And it's very useful both from a technological and sort of fundamental research point of view. For example, by using the nonlinear current voltage relation of the Josephson junction, it can be used as a superconducting qubits. By using the phase dynamics, basically the AC Josephson effect of the junction, it could either be used as a photodetector or to generate very high frequency electromagnetic waves. And fundamentally, if you bias a certain type of junction with some kind of a phase correctly, you can get some kind of topological superconductivity. And also more recently with sort of engineered or intrinsic symmetry breaking, you can have the Josephson diode effect, which is essentially, the asymmetric forward and backward critical current of the junction. Okay, so the basics of the Josephson junction is like this, right? So you take two superconductors and you have some non-superconducting material in the middle. And the wave function of the superconductor will tunnel into this normal metal and they will interfere, which causes the supercurrent to flow in the metal. And the Josephson current is essentially, given by the sign of the phase difference between these two superconductors. As you can see here, this current is sort of defined by the limit, which is the critical current, below which all we can measure is a zero resistance. right? So that is kind of the problem. So the junction we're going to study in our case will be a planar junction, right? So I can take the model on the previous slide and sort of extend it on the 2D plane. So essentially, we can have these two pieces of superconductors sort of sandwiching this normal material. And the junction can be, put under a perpendicular magnetic field, perpendicular to a plane. So in this case, the current density along the x direction of the junction is also given by the sinusoidal current phase relation, whereas phase now has two components, right? So now first is the superconducting, the phase difference between the superconducting electrodes, delta phi. And the second part is the sort of the phase induced by this perpendicular magnetic field, right? And it could take some complicated form, but in general, it's something that's proportional to the external field. And so, the total current, the total DC current is then nothing more than the integral of the current density. And now if you take a transport measurement, what you get is as a function of, DC bias as well as magnetic field, what you get is this so-called sort of Fraunhofer pattern, right? Basically, it's the oscillating of the critical current as a function of the perpendicular magnetic field. And you can sort of fit, with your very simple model, and you can see, okay, like the critical current can be fit with this, sort of oscillating function. And interestingly, like this function, this critical current actually has two nodes, right? It's a positive node and a negative node. And they will sort of meet at these, magnetic field points where the critical current goes to 0. So you can say, okay, maybe this looks all very good. Like this is a very standard junction. Everything looks great. It seems like we understand everything. Maybe a little bit of a detail, where not sort of understood is like the critical current doesn't fit the model. But things can get actually very complicated very fast in sort of more realistic, more complicated Josephson junctions, right? And here are a few examples. So by no means are these devices not good, right? So they're all very high quality devices. But if the material in the middle of the junction, for example, is more complicated, or you have sort of non-trivial geometry of the junction, then the critical current can become not closing the node of the critical current not happening, or the periodicity of the node becomes aperiodic. So overall, this is to say that we need some alternative observables to characterize our Josephson junctions, particularly when we're in the zero resistance state, right, below the critical current. Okay, so this will be the outline of my talk. I will first introduce to you the technique we're using to visualize the Josephson current, and I will sort of discuss two examples of what we can actually learn from this. Okay, so the sensor we're going to use here is the nitrogen vacancy centering diamond. So the nitrogen vacancy center is exactly the name as the name sounds. It's a nitrogen atom, substitute a carbon atom, and also a absence of a carbon atom in diamond. And it will be able to measure this magnetic field along this direction, which is the 1-1 direction of the tetrahedral diamond. So we can put this NV center on the apex of a tip and try to measure our planar Josephson junction, right? So the planar Josephson junction we have in this case is a superconducting normal superconducting junction, and the superconducting material is just niobium, and the normal part is just gold, right? So it's actually a very, very simple SNS junction. And here are some of the sort of parameters of the junction. And so how does the NV actually measure the magnetic field, right? So basically for the NV center, it's a spin-1 system. So with the external magnetic field, the Zeeman field will be able to split the plus and minus 1 state. And you can pick either one of them and the 0 state to form a 2-level system, right? And by looking at the level spacing, you can use it as a DC magnetometer, which can measure the magnetic field in the real units of Tesla. And an alternative way to use this is to use the AC magnetometry of the NV center. And to do that, what you can do is, you can put your spinner on the equator of this block sphere. And in each half of this AC cycle, the magnetic field will be able to drive the NV center, and the NV center will, the spinner will accumulate a rotation angle that is proportional to the magnetic field. And because this angle is flipped in the middle, so basically in the end, what we can measure is the differential signal between the first and the second half of the cycle, right? So for example, if I use some current, and the current will generate the magnetic field, and I will be able to pick up the difference of the signal I put in each half of the cycle. Okay, so a little bit more technical. So how does a diamond sort of come together? So actually we can have a we can have a diamond slab, and on top of it have a little diamond pillar. And actually, the pillar will serve as a very nice waveguide for the light, so we can initialize and also create the photoluminescence from the NV center. And everything is glued to a tuning fork, so we can do AFM measurements on surfaces. Okay, so before I start, with our junction, I think with the superconductor, there's actually something very important that, as experiments, we should always ask, kind of when we're dealing with superconductors, and that is regarding the thickness of the superconductor. So we all know that the superconductor has a Meissner effect, which means that it screens the external field, right? But this only sort of applies when the superconductor is bulky, right? So you can have like a lot of screening current and can fully screen the external magnetic field. However, when you have a very thin superconductor, actually the current in the superconductor is not enough to screen the external field, and actually the field can still penetrate in the middle of the superconductor. And to distinguish between bulk and thin, it's actually you can do that by comparing the size of your superconductor with the so-called Pearl length. If the Pearl length is much larger than the size of the device, the size of the superconductor, then we're in this thin film regime. Right, so we can actually know this by directly measuring with our NV center using the DC magnetometry by taking a line cut along our superconductor and measure what is the Meissner field generated by the supercurrent. And from this data, do a line fit to retrieve what is the Pearl length in our superconductor. And we find actually for the devices we're measuring, we have a Pearl length that's actually larger than the device size, which means we're in the thin film regime where this phase of the Josephson junction is given by this equation. I see there's a chat question. Are BX, BY, BZ generated by the current all measured by the NV? Yes. So if I go back a little bit, oops. So yes, so the NV center will be able to pick up along this direction, which is indeed not in the perpendicular direction. It's like 60 degrees, relative to the plane. So yes, it will be able to pick up the XYZ direction of the magnetic field generated by the current.
So I have a question on the slide you just flashed back. So about the AC measurements. Sure. I just want to clarify. Do you need to have it to be like pi phase shift, or it can be arbitrary or like phase? Because you show like pi over 2 and y pi. Does that mean you need the phase to be quantized? How?
So yeah, so the measurement phase does not need to be quantized. So this is a microwave control sequence, right, which controls how. Yeah, so the measurement can be whatever.
Okay, you use this like pi over 2 or pi phase to make sure there will be some coherence for you to pick up the signal.
Right. This is to drive the NV center, yes. And
I see. Yeah. I see. Thank you.
Okay. All right. So now we can sort of think more about, okay, so what we can actually measure from the Josephson junction, the current flow in the Josephson junction. And again, this is the current phase relation as we saw before. We have these two terms, and we'll start by looking at the first term, delta phi, right, which is the phase difference between the superconducting electrodes. And we can consider a case of some finite magnetic field, right, such that we'll have some curvature in the current. So if we take the limit of, take the case of zero phase difference between the superconductors, this is what is the current flow I would expect in the junction. And because of the magnetic field, actually, even if I don't have any, and actually in this case, the total bias current is 0, right? If you integrate this curve, you get 0, which means even if I don't have any external current bias, I can still have locally at the junction some current flow induced by the external magnetic field, right? So that is a persistent current at the junction. And now if I change delta phi, essentially what I'm doing here is shifting this curve towards one side of the screen, right? So for example, when I'm at pi over 2, I reach the positive critical current of the junction, and the current profile will look like this. And then we can sort of plot it out, right? So we can either sweep going to the positive critical current or the negative critical current. Then essentially the profile of the current will shift left and right on the junction. And in particular, when at the minus critical current, then the phase difference is minus pi over 2, and the positive is positive pi over 2. So this means that essentially we can use our bias current to change the phase difference between the two superconductors. That's how the first term can be changed. And to visualize this effect, we will do this. We'll do an AC measurement that takes the difference of a zero bias of with a finite bias. So in theory, what this looks like is essentially I can subtract from each of these curves in my theory with the bold line in the middle, which is a zero bias case. And this is the result I get in the bottom panel. This is what I expect for the current flow. And in our measurement, what we can actually do is to take a 2D map of the junction area. Right, so let me explain this a little bit. So in this plot, the solid lines are the superconducting electrodes. The dashed line is the metal that forms the normal part of the junction. And this color you're seeing is the Z component of the magnetic field generated by the AC current flow. Right, so going back to that question, the MV center will measure the XYZ component. So it's measuring the projected field along the MV direction, which we can reconstruct to get only the Z component of that magnetic field. And the arrow in this case is showing the current flow, the vector of the current flow. Right, so I'm showing these two cases for either a negative bias current or a positive bias current, and you can see that they're actually very different as we expect from this case. And if we take a line cut of the current profile at the center of the junction, then you can see indeed they actually fit very well with either a minus bias current case or a positive bias current case. And from the shape of this curve, I can also fit delta phi to get this number. And if we measure this as a function of the bias current, we can see indeed it can agree with the sinusoidal current phase relation that we assumed. Okay, so that is for delta phi. We see that part first. And in the second part, we can see how the magnetic field changes the current flow in the junction. So basically, we can have this phase, which is proportional to the magnetic field. So as we ramp up the field, the current profile becomes more and more squeezed. And realistically, what that means is that we'll be starting to introduce vortices in the junction. Right, so the previous case, we have a zero vortex in the junction, or you can think about this as a Meissner state of the junction. And as we ramp up the magnetic field, we introduce a vortex, which is a current loop in the junction. And again, if we look at the line cut of the current profile, what you could expect in theory is like this, as you saw before. And as in the case of having a one Josephson vortex in the junction, the current will actually change its sign. And that is because of the pi phase shift that is associated with the junction. Right, so you may think this is actually pretty simple, but surprisingly, this has not really been observed before, in terms of the Josephson vortex current flow in the junction. Okay, so to visualize this, what we'll do is to do using a different AC sequence to do the measurement. Now we will take the difference of sort of symmetric plus and minus bias current and measure the signal. Right, so the left panel you have seen before. So in the middle panel here, I'm showing what is the expected case for using a plus bias minus a minus symmetric bias. And you can see the line shape becomes more symmetric and it will sort of grow in amplitude as a function of this absolute value of the bias. And in our measurement, again, we'll take a 2D spatial map in the case of either zero Josephson vortex or one Josephson vortex. You can sort of see that the background of these two cases are the same, right? Because we're applying the same direction of the external bias. But the signal at the junction is reversed, right? So in the zero Josephson vortex case, we have plus and minus, and in the one vortex case, we have minus and plus. This suggests that, again, if we take a line cut, we indeed see this reversal of the current direction inside of the Josephson junction. Okay, and from this, I can try to get something a little bit more quantitative, right? So as I mentioned, that the phi of E term essentially controls the shape of my current profile. So if we only look at the case at the critical current, right, which corresponds to this of the delta phi, then essentially the current profile looks like a cosine function, right? And as I ramp up the magnetic field, the cosine function gets more and more squeezed, and the oscillation becomes the periodicity of the oscillation becomes smaller and smaller. And from this, I can try to fit the shape of my measured current profile and try to get what is the magnetic field, for example. So first of all, if I use the magnetic field that is the external magnetic field, right, in this case, and try to plot my expectation, and you can see actually it does not agree with the measurement data, right? And but now we can use this entire term as a free variable, free fitting parameter, and try to fit what is the effective phase. and do this as a function of external magnetic field. And what we find is that in the case of a zero vortex in the junction, that my expected phase is always lower than the external phase. Whereas if I have one vortex in the junction, then my expected phase, then my effective phase is higher than the expected phase. So this is pretty weird. You would think, okay, so why is this? What is going on here? So we have so essentially what we have here is some kind of a self-induced phase because of either 0 or 1 Josephson vortex, right? And you may think, okay, this is because of, okay, so we have some current flow in the junction, so the current will generate a magnetic field, and those magnetic field will either add to or cancel the external field. And this is sort of what's being proposed mostly in the literature, which is a so-called self-field effect. But if you remember, as I told you, our superconductor, our junction is in the thin film limit, right? Which means the current generated magnetic field is actually very small, not enough to sort of cancel or add to the external field. So it cannot be the self-field effect. So to understand this, we need to examine a little bit more carefully, how the phase is induced in the thin film Josephson junction. And so the idea is this: so under the external magnetic field, right, the current in the there will be a screening current inside the superconductor, and particularly at the junction, there will be sort of this counterflow current indicated by this red arrow, and the flow of the current will create a phase gradient, of the superconducting phase inside the superconductor. And the phi of E term that we use in our junction is nothing but the difference between the phase along the left side of the junction and the right side of the junction, right? So basically, in the thin film Josephson junction, the phase difference is actually controlled by the screening current. And now, if we introduce the Josephson current, right? So the equation was derived in the case of neglecting any Josephson current going across the junction. But now if we introduce the current again going across the junction, because of the continuity of the current, you can see that the screening current at the top and the bottom of the junction will be either reduced in the 0 vortex case or increased in the 1 vortex case. This means that essentially our Josephson current will also change the screening current and thus changing the effective phase across the junction, right? So we can do some simulation and indeed see that, for 0 and 1 vortex case, the phase across the junction is different. And this is, essentially a phase that is induced by the kinetic inductance of the thin film, because this phase gradient of the superconducting phase is proportional to the kinetic inductance times the screening current. Okay, so this is the first part. As I showed you, like we can essentially see what is going on inside the Josephson Josephson junction, what is the current flow. And by and large, we see that, bias current can control the phase difference, the magnetic field flux can control the Josephson vortex, and everything is more or less as expected, maybe with some small caveat. But now we can see that we can push the conditions to be far from the basic case, and the things become pretty different. So that's the second part. So essentially what we can do here is by, we can drive up this Josephson current, and which will increase the induced phase from the induced phase. Right, so this is showing the simulation, showing the two cases. In a weak junction, we have a little bit of a difference, for example, between the 0 and 1 Josephson vortex case. But if we really crank up the Josephson current, we have a huge difference between these two states. Right, so this is the so-called strong junction regime, which we're gonna see next. And we can simply do this experimentally by measuring our device at a slightly lower temperature, right? So the data I showed you before was measured at 7 Kelvin. If I just cool to 4 Kelvin, then you can see, again, from transport, that the critical current on my junction already increased by an order of magnitude. And from the Fraunhofer map, what is different is that indeed you can see these, the nodes of the critical current has been lifted. And everything below the critical current is zero resistance. So it's kind of a mystery what is actually going on, what is causing the node to lift. So to understand this, what we can do is to do a local magnetic field imaging measurement, but sort of taking a similar data as the transport. So in this transport measurement, what we are doing is taking the differential resistance of the junction, right, dV over di. And again, everything below the critical current is 0. So what we can do with our MV center is we can park our MV center somewhere, over the junction area, and try to measure the local magnetic field generated by the current. And we'll be using a sequence that takes the difference of two slightly different current bias, which means essentially we're doing a DC plus AC measurement, and we'll be able to pick up this the AC magnetic field signal generated by this small AC current. And we'll zoom into this part on the phase diagram, right? So the magnetic field and the EC bias range. And this is the result we get from the MV center. You can sort of see a lot of features. And let me just first, by overlaying the critical current measured from the transport, right? Just bring in this over here. And we can see these larger, these features at the larger DC bias corresponds to the critical current. But there's also this additional boundary which happens below the critical current, right? And as we'll see in a minute, this essentially separates a 0 Josephson vortex and a 1 Josephson vortex regime under the critical current. And we can also do a similar measurement for this region where we have 1 or 2 vortex, and we can see a similar boundary between a bit below the critical current of the junction. And I want to mention that we also tried measuring this by reversing either the magnetic field sweeping direction or the DC currents sweeping direction, but we get very similar results. Okay, so let me show you the evidence of, this is 0 and the 1 Josephson vortex. So what we can do is, we again use the same sequence to measure the local AC magnetic field generated by the AC current, but now take a spatial map, right? Either at this part of the phase diagram or inside this part of the phase diagram. And we see very different features. Indeed, in the first part, we see almost featureless, which corresponds to a 0 vortex state. And in the second part, we see this, double loop feature, which is reminiscent of what you saw before of the 1 Josephson vortex case. And if now I actually in the 2 half of my cycle, I taking the difference of the 0 and the 1 Josephson vortex state, then I can get the full profile of the vortex, right? As you see here. So what this tells us is that in this case, we can electrically drive a switching between the 0 and 1 Josephson vortex case, all under the critical current and without any need to change the magnetic field. Okay, so a little bit surprising here is that what is actually going on in this phase boundary of the 0 and 1 Josephson vortex. And to understand this, we carried out time-dependent Gainsborough-London simulations. So essentially, by choosing a different initial condition, we can either realize a 1 Josephson vortex state or 0 Josephson vortex state. And we can plot the critical current of either state as a function of magnetic field and DC bias, and this is what you see. So essentially, there will be some overlapping area where either 0 or 1 Josephson vortex states are possible. So essentially, in this area, there are 2 local energy minimum with respect to the wave function of the superconductor, if you will. So in the simulation, actually, it tells us there are supposed to be 2 boundaries, right? But in the experiment, actually, we only observe, this 1 boundary, which corresponds to, the 1 Josephson vortex state. And that is a little bit surprising because, in the overlap region, what you would expect is hysteresis. But maybe one thing we can try to understand is a little bit is to take a look at the energy difference of the 1 and 0 Josephson vortex state. So the orange color here indicates that the 1 Josephson vortex has lower total energy, and the purple corresponds to the 0 Josephson vortex having lower energy. You can see that in the majority of this overlap area, we actually have indeed energetically the 1 Josephson vortex states winning. Although I do concede that the lack of hysteresis is a little bit unexpected. Okay, so another feature you can sort of see from either the experiment or the simulation is that the feature is actually asymmetric with positive and negative bias current, right? And that is actually intentional in the simulation and can be understood in the experiment. And particularly if you look at, for example, here at this magnetic field, you will find that a positive and negative bias, positive critical current and negative critical current are actually not symmetric. So this is a so-called Josephson diode effect, which describes essentially if you pass the current in one direction, you can get a superconducting state. If you pass the current in the other direction, you can get a resistive state. And just by symmetry, we understand that time reversal symmetry and the inversion symmetry must be broken in order for the critical current to be non-reciprocal. So the time reversal symmetry obviously is broken by the magnetic field, but what is breaking the inversion symmetry? And are these 2 enough to lead to the Josephson diode effect as we observed? So this will be the last part of my my talk. So we can look at the transport data as I just showed you, the 7K and 4 Kelvin data, taking a look at the critical current. And what you can see is here here is actually in the 7 Kelvin data, data is a bit noisy, but essentially the critical current is actually pretty symmetric for positive and the negative. Whereas at 4 Kelvin, indeed, you can see the diode effect, which is illustrated by this asymmetric factor of the positive and negative critical current. So the first question is, how do we actually have the inversion symmetry breaking in the junction? Or so it turns out that we do have inversion symmetry in the breaking in the junction, which we can also directly see with the current. And in the 7 Kelvin case, this can actually be seen by the data I already showed you, which is taking the difference of the symmetric positive and negative bias. If you take a line cut, of the current profile across the junction, you can see that actually the line profile is not symmetric, right? The shoulder is lower here in the 0 vortex case, and it's higher here in the 1 vortex case, which suggests already that the critical current density across the junction along the junction, is actually not uniform. And in the 4 Kelvin case, we can do additional measurements. Now, just taking this, the magnetic field generated by the small AC current, and do that at either a positive or a negative bias. And if the junction were perfectly inversion symmetric, what you would expect in this case is the shape of the current should be inversion symmetric with respect to one another. However, that is not what we see. We can sort of see a loop here and no loop in the minus case. And that is confirmed by our simulation, in which we introduce a small tilt of the junction width to sort of model this asymmetric effect of the junction. So basically, with direct measurement of the current flow, we can confirm that indeed there is although unintentional, inversion symmetry breaking in the junction. But however, essentially what we're saying is, okay, so both at 7 Kelvin and 4 Kelvin, we have inversion symmetry and time reversal symmetry breaking, but that is actually not enough to cause the diode effect, because we don't see that at 7 Kelvin, but we do see it at 4 Kelvin. And the difference here is really how strong our junction is, or how strong this Josephson current induced phase is, or how strong the kinetic inductance effect is. So what we can show with kind of not very complicated modeling is that essentially, if we have a very strong phase gradient induced by this Josephson current, then in the current phase relationship of the junction, we can have a second harmonic term that also has a phase difference in it from the first harmonic term. So this basically forms a basic model to realize a asymmetric critical current for the positive and negative bias. So we think this here is our new mechanism for the Josephson diode effect, which can essentially be realized even if the current phase relationship of the junction itself is only first harmonic, but the second harmonic with the phase shift can be introduced by the kinetic inductance effect. Okay, so that is my talk. Hopefully I've convinced you that we have a very nice technique to visualize the current flow, particularly in superconductors, and we were able to review these sort of hidden states that are otherwise not observable with transport or otherwise. Okay, so with that, I would like to thank all my collaborators and happy to take any additional questions you might have. Thank you.
Thank you, Shaowen. Thank you for the excellent talk. And now the floor is open for questions. Okay, let me start off with one quick question. Perhaps I may have missed it. What kind of spatial depth do you think this could achieve? And also in terms of lateral resolution, I think you've already shown excellent statistics there, but yeah, if you'd like to comment on that.
Yeah, so I think like the spatial resolution in our current version of the measurement is on the order of 100 nanometer. I'm not sure what you mean by depth. So essentially what happens is that the NV center is hovering kind of, basically 100 nanometer from the surface. So that is what is limiting the spatial resolution.
Right.
Yeah.
Thank you.
So I see a raised hand.
Yeah.
Hello.
Hey, yes.
Just a silly question. Are there any ways to stabilize doubly quantized vortices in these junctions? And if so, I'm guessing your NV center could check if you made one.
Doubly, could you say it again? Doubly
Sorry, I was
quantized?
just wondering, I'm a bit ignorant of single vortices and junctions. I'm just asking, is there a way to stabilize doubly quantized vortices? And if so, I'm guessing.
So like a 4 pi vortex or something, or
yeah, doubly quantized. Like they're theoretically possible. They're just almost never stable compared to two singly quantized.
I'm not sure. I think one thing we can think about is, for example, again, by having this very strong like a current induced effect, for example, right? So I think in the basic case, for example, if we only have a sinusoidal current phase relation, if the phase is like spatially kind of linear, then there's no way for that to happen. I think it's very hard. But if we have a very strong kind of a nonlinear effect, if you will, for the phase as a function of space, then I don't know exactly how we will do it, but I think that's possible.
Right.
Yeah.
Thank you.
I have a quick question.
Yeah.
First of all, very nice talk. I really enjoyed it. So
thank you. Yeah.
my question is, so I know that Aries and near Kobe, I think that was back in the days where they were studying the such type of junctions for creating localized Majorana modes at the junctions. So I was wondering whether there are any non-trivial features that you can visualize in this technique.
Yeah, so this is something we're also thinking about. My understanding now is that, yes, there might be, so essentially what the Majorana could do, I guess, in theory, is that it will lead to, it can sort of generate a sort of a non-trivial current phase relation, right? I think that's kind of the basic understanding. So for example, instead of a 2 pi periodicity, like a sine phi term in the current phase relation, you might expect a 4 pi term. And I think that's essentially that will manifest in the current distribution, because essentially, yeah, the current distribution will be different. But I think in terms of detail, we're thinking more about it. Yeah, and I think it's also kind of theoretically maybe nice to think about to have some more understanding. Yeah.
Any other questions? Okay. I think, yeah, I think we don't have any more questions. Excellent. Let's thank Shaowen once again by show of virtual claps. Thank you, Shaowen, and we look forward to seeing you all. Thank you. We look forward to seeing you all at our seminar a month from today. We'll send you reminders as we get close to it. Our next speaker will be Xiaoyu Wang. So yeah, thank you again. Bye.
Yeah, thank you, everyone.